Hello and welcome back. In today's video we are going to start with another classification, that's internal versus external flow. So an internal flow is the one in which fluid is confined by walls. The shape of the cross section can be anything. The flow is considered to be internal if the fluid is confined by the walls fully. So like the pipe flows, duct flows, etc. These are internal flows, and it's important that the cross section, entire pipe or entire duct is filled with the fluid. Then it's called internal flow. If fluid is confined by the wall like pipe, but it is half or partially filled by the fluid and there is a free surface like this, so this is classified as open channel flow, not internal flow. Open channel flow, or we can call it a special type of internal flow because there is free surface. If it is fully filled with liquid, then we call them internal flow. Internal flow. Now internal flows can be laminar or turbulent. Let's start with viscous and non-viscous. Now internal flows are always dominated by viscous effects, so there is nothing like no such thing like inviscid internal flow. Internal flows are always viscosity dominated, so they are always viscous. So they can be laminar or turbulent. So if internal flow, we want to find whether this internal flow is laminar, it's always viscous. So what is this, laminar or is turbulent? We use critical Reynolds number for internal flow, which is if the Reynolds number is less than or equal to 2300, the internal flow is treated as laminar, and if it is greater than say 4000, it is turbulent. And if it's in between, it is transitional flow. It is transitioning from being laminar to turbulent. And this is the case for internal flows. And since internal flow can be laminar or it can be turbulent, it can also be compressible, incompressible. Compressible, incompressible. So internal flows can also be compressible, they can also be incompressible. If density changes are significant, then compressible. If density changes are insignificant, so we classify it as incompressible internal flow. Now external flow. Now if unbounded fluid, here fluid is bounded by the walls completely. If unbounded fluid passes over a body of any shape, it's called external flow. External flow of any shape. It can be a sphere, it can be a cylindrical object, it can be a flat plate, it can be a body of any shape. For example, it can be an aeroplane. It can be an aeroplane, something like this. So flow, for example, airplane passing through the air is an example of external flow. Air is flowing over it. We throw a ball is an example of external flow. We kick a football or whatever object. So these are all examples of external flows. A car moves on a road. The air is flowing on the opposite side over the car. That's the example of external flow. See, these are all examples of external flows. And if we take an example of flat plate over which fluid is flowing, This is a simple case of external flow. Now, for this simple geometry of flat plate, external flow can also be laminar-turbulent, just like internal flows, and it can be compressible-incompressible in the same way. Now, for a flat plate, the Reynolds number, critical Reynolds number, is taken as 5 times 10 to the power 5. If for a flat plate, in case of external flow, if Reynolds number is less than 5 times 10 to the power 5, less than this critical Reynolds number, it is treated as laminar external flow, and if it is greater than this number, it is treated as turbulent external flow. So in case of internal flows, we remember this number, and in case of external flow, we have to remember this number. In case of external flow with a flat plate, this is important, because the critical number will change where if we take a sphere in case of a flat plate, or we take a cylinder in case of flat plate, or any different geometry. And as I said, external flows can also be compressible, external flows can also be incompressible depending upon the density changes. And usually one more important thing that I said is internal flows are always viscous dominated. They are always viscous, they are not inviscid. But external flows are mainly inviscid. External flows are mainly inviscid, but there are two regions where viscous effects are dominant, and we have to consider those regions of flow as being viscous regions of flow. And those regions are flow near the wall of the body and flow and behind this object, this region called wake. Here viscous effects are high, they are dominant, and this layer of fluid, thin layer of fluid around the body, we call it boundary layer. So viscous effects are dominant in case of external flows in two regions. One is the wake region behind the body, and another is this thin layer on the wall of the object, which is called a boundary layer. So external flows are and the outside, all other regions outside the body is considered as inviscid region of flow, where viscosity is neglected. And this inviscid can be compressible and incompressible, as I said. Now these viscous regions of flow can be laminar, can be turbulent. And one more thing that we have to remember here is, since we talk about a boundary layer, this thin layer itself can be laminar boundary layer, it can be turbulent boundary layer. So we have to take care of those. When we study the boundary layer theory, we have different equations. If the boundary layer is laminar, we use simpler forms. If the boundary layer is turbulent, we use more difficult forms of equations that we analyze for a problem. So this was all about internal versus external flows. So internal flows are those flows which are completely bounded by walls of any shape. We call them internal flows. Internal flows are always viscous dominated, they are not inviscid. Now since they are viscous dominated, they can be laminar, they can be turbulent, this is the criteria. And they can also be compressible, incompressible, depending upon density change, whether it is significant or not. And a special case of internal is open channel flow that takes its own chapter. If it is partially filled with liquid, we call them open channel flows or free flows. For example, flows in rivers are open channels, flows in irrigation channels, they are open channel flows. They are gravity dominated, so we study them in separate subject. Now they can also be compressible and incompressible, and their being laminar or turbulent is decided by this critical Reynolds number. Now external flows in which this unbounded fluid flows over the body of any shape is the external flow. Now external flows can be can have both regions, or actually they have both the regions. They are mainly inviscid outside the body, but they are viscous dominated in two regions, which is near the wall, this thin layer that touches the wall. Their viscosity effects are significant, and the region behind the ball is called the wake. In these two regions the viscous effects are dominant, and they can be laminar or turbulent. So these two regions can be laminar, can be turbulent. Just like I said, boundary layer can be laminar, boundary layer can be turbulent, which is also important to deal with separate types of theories: laminar boundary layer theory, turbulent boundary layer theory.